So last class period, we started section 1.1, mathematics and problem solving. We talked about some problem solving strategies in particular, a problem solving method, a four-step method. And we had done one particular problem that hopefully was a little bit new to most of you, which was, I referenced it as Gauss's problem. But what we're going to look at next is extension of Gauss's problem. So let me just remind you what we did with Gauss's problem because we're going to revisit it very quickly. So Gauss's problem was the idea of how do we add the numbers 1 to 100 together in a more efficient way. That's really what it's about. And so what we can do is we can take the order of our numbers, we can reverse it and add it to the numbers we started with. That doubles the amount that we have. But what it does is it creates add-ins as we sum them down that are all identical. So this one was 101. So they're all 101s. We had to figure out how many of them we had. Then we were able to multiply the number we had times the number 101 and then divide by 2 to remove the double counting. So it ends up giving us our answer lots more quickly than going 1 plus 2 plus 3 plus 4 plus 5 and so on. So we're going to extend this idea, and instead on this one we're going to take a look at the numbers from 36 to 147. All right, so one of the things that you probably should notice is that they're not skipping any numbers. I'm going to tell you what to do, what happens basically when you skip numbers in a little bit, because you will see some of those in your homework. But this one doesn't skip numbers. So that makes it more like the one we just did than some of the ones you'll see in your homework. However, it does not start at the number 1, right? Okay, so the same basic idea is going to play out. We're adding the numbers together. So 36, 37, 38. And it goes to 146, 147. If you want to put the 145 in there, you can. It's really not a big deal. And we're going to do the same thing Gauss did, whereas we're going to add them to them reversed. Okay, so we're going to add to this basically the same thing, but in the opposite order. So here's 147 first, and then 146. And then it's going to continue down, and then our last numbers are going to be 37 and 36. Okay, so again, just like Gauss, we're going to add the digits down, and we're going to notice that there's a pattern that happens. So what is 147 plus 1 plus 36? How much? 183. Okay, so are they all 183 as you keep going with that? Okay, so if it's going to follow Gauss's, that's the idea, is they all need to be the same thing, and they are. And of course, that's double what we started with because we added the list to itself. Okay, so the part where students will often make mistakes is figuring out how many of these there are. Okay, so I have the numbers from 36 to 147. Any ideas of how I could easily find, or maybe easily find, how many numbers there are?
147 minus 36.
Okay, so you guys are really close, and that's what everybody always wants to tell me, is that it's 147 minus 36. Okay, so if that's true, let's go back to Gauss. What you did is you took the last number minus the first number, and what do you see? We're missing one, right? So you're really close. You're definitely on the right track, but instead of subtracting the first number, we actually want to subtract what comes before it. So in this case, what we really should have had here is we should have subtracted the number 0, and that would have given me 100. So over here, what I really want to subtract, and I'll explain why here in just a second, is the number 35, not 36. So what's 147 minus 35? 112. Okay, so let me briefly tell you a justification, at least, for why we would want to subtract the number before. Let's pretend the numbers actually started at 1. If you went from 1 to 147, there would be 147 numbers, right? Okay? But we don't have the first 35. That's why we're subtracting 35. We're not subtracting 36 because the 36th one is in my list of numbers. It's included. I need to take off the ones that are not included, which would end at 35. Okay? So you're right, there's 112 numbers. So we'll take that sum, 183, that we keep getting. We'll multiply it by the 112. Somebody's going to undoubtedly find that value for us with the calculator, right? I have one out for today.
20,496.
Okay. And then what do you think we need to do? Divided by 2. And again, why are we dividing by 2? Where did that 2 come from? It came from 2s, but where did the 2s come from? Why did the s become 2s again? Yeah, we added it to itself. We doubled our value when we did that addition step. Good. So when we divide by 2, what do we get? 10,000 something.
10,248.
Right. Excellent. So let's just talk for a second about what would happen if numbers skipped. Okay? Doesn't really matter where they start and the where they end. We've addressed how we deal with that, right? You subtract the number that came before it. So let me create just a very short sequence of numbers where we skip something so you can see the difference in what happens. So how many numbers you skip plays a role. So let's say, for instance, we had, we'll start with 15, 20, 25, 30, and I'm just going to stop at 35 because I don't need a long list to be able to show you what's happening. How many are we skipping by each time? 5. And it doesn't have to be multiples of 5. Like I did multiples of 5 here, but it could have gone 16, 21, 26, 31, 36. I'd still be skipping by 5s, okay? So I'm skip counting. That's what that's called if you remember that phrase. So I'm skip counting by 5. So I'm just going to make a note of that. So when I'm taking these numbers and I'm adding them to themselves, just like in the other options that I did before, so I would have 35 down to 15, okay? So we're adding all these numbers together. They should all have addition signs in between it. I'm not doing a full-fledged example, but do you have the right idea, okay? So I'm still doing the adding together. I'd be getting 50 on all of them, like so, okay? And I'd have my doubles here because I doubled my list by adding it to itself, okay? So when I'm looking at this list, there's one nuance first that I want you to notice. I realize we can count 15, 20, 25, 30, 35. I know I have 5 numbers. I get that. But usually you've got the dot, dot, dots in the middle, and you can't just count them up quite that easily. So a moment ago, what we said is we take the last number, which is true, 35, and we subtract the number before the first number. But it needs to be the number before the first number in the pattern. Right? So I'm not going to subtract 14. That's not a part of my pattern. What number should I be subtracting? 10. But notice, if I do that, I get 25. There are not 25 numbers. So what do you think I need to do to actually get the right number of numbers? Right? It should be 5. Right? We counted. There's 5 numbers in this list. You're close. We are going to divide it by 5. But it's not because there's 5 numbers. It's because that's what we're skip counting by. Yeah. So I only have every 5th number. So my 25 down here is going to end up being divided by 5 because there's only every 5th number. If I were skip counting by 3s, I'd divide by 3. If I were skip counting by 2s, I would divide by 2. So my number of numbers is altered because of the skip counting business. Okay, and you are going to have at least a couple places where they're going to ask you to find a sum where it skip counts by either 2s or 3s. I can't remember which one it is. It may be one of each. So you would do your 2s here. That looks kind of like a 5. A 2s here. You'd have the 50. You'd multiply it by 5 numbers, right? Because there's really only 5 numbers. And then you divide by 2 and we'd be done. Okay. Something to keep in mind. If you get a decimal when you do that division by 2, there's an error somewhere. Why can I say that for sure? Okay, it has to go back to the normal number. And what do you know about the normal, like the original number? What does the sum have to be? Has to be a whole number. In this case, it would be increments of 5, but in general, it has to be a whole number. And it has to be a whole number because when you add whole numbers together, you get other whole numbers, right? That is a property we haven't actually discussed. We will discuss, but it's something you know to be true. No child learns addition in first grade and somehow ends up with a decimal answer, right? No, it doesn't work like that. There's a reason why, but it doesn't. So anytime you work these problems, if you do end up finding yourself with a decimal answer, it should red flag you that you need to go back and take a look at what mistake you've made, because there's a mistake somewhere, and it may just be a data entry mistake in your calculator, right? Like, that's a possibility. But there is a mistake somewhere to be had and found, okay? All right, let's take a look at another kind of example. I mentioned this one last time, scheduling. So this is super practical stuff. Scheduling soccer leagues or basketball leagues. YMCA does this, every time they have a sport that they're running. So on this scenario, it says a soccer league has 10 teams, and each team plays every other team once. How many games will the league manager need to schedule at the start of the season? So, if you weren't sure, you could probably make a list of all these numbers out. 10's not extremely large. That would be a viable option on how to solve this problem. It would. But if you had 20 teams or 30 teams, it becomes a less viable option every time, right? So I'd like to show you what happens when something's large enough that it's not practical to write it all out. Not because you couldn't on this one, but because sometimes it's not practical. And you're going to find this one's probably more than you would have imagined. So we're going to pretend for the moment that we only had 3 teams. And I'm going to call the teams A, B, C. And we're going to do exactly what I suggested, like listing everything out, but we're only going to do it with 3 teams instead of 10. That'll be much quicker. So if we do this, we can start with team A. So team A has to play team B. That makes sense. Team A has to also play team C. And actually, if they only play once, there are no more games for team A, right? Yeah, that's true. I am missing something, though. B and C haven't played as I've written them down right now. Okay. There's 3 games. So I have 3 teams, there's 3 games. Unfortunately, if you do 4 teams, you won't find that it's 4 games, which you might think, is the pattern that's started developing here. It doesn't work. So what I'd like for you to see happens on this is a pairing idea. So you've probably heard of, it's usually thought of as a riddle. Like 100 people go into a room, how many handshakes are there if everybody shakes hands with every other person in the room? This is the same thing. It's just that it's 100 people instead of 10 teams. Okay, so it's this idea of how many pairings can I have happen, right? So while I could pair up the numbers A and B, or the teams A and B, I could also pair them up as teams BA, right? Like if I'm trying to consider all the games that could be played from each team's perspective, well, team A has, in fact, let me write it this way. Team A is AB and AC. Team B is BA and BC. Team C is CA and CB. Okay? So I'm looking at their list. There's on the list from Team A, they've got this list. And on the list for Team B, they've got this list. And on the list for Team C, they've got this list. Everybody good so far? So there are 6 if I consider it from this perspective. So why are there 6? Because there are 3 teams, and each team plays 2 games. Right? They play each of the other 2 teams. But this would be 6, which is what I have listed here. And we should hopefully notice pretty quickly that there's some games here that I've listed twice. If they're only going to play each other once, then BA and AB both don't need to be there. And CA and AC don't both need to be there. And CB and BC don't both need to be there. It's much like this over here. There's a double count in it. Because I counted it when I listed out all the games that Team A played, and I counted it when I listed all the times that Team B played, and so forth for each of the team's pairings. So what happens is I have to remove the double countings. So I end up having to remove the fact that I counted everything twice. So if you think about it in that way, you have 10 teams. So here's my 10 teams now. There are 10 teams. How many games does each team play? 9. Each team has 9 games that they're going to play. But if I list it all out, 10 times 9, just like I did the 2 times 3, I would end up double counting all the games, right? Because it's on my list and it's on my opposing team's list for every single one of my opposing teams. I would list, it would be doubled. So I have to remove the double counts by dividing by 2 because everything's doubled. So if you do 10 times 9, what do you get? 90, and 90 divided by 2 is 45. So there are 45 games that this person needs to schedule for the soccer league. The next one's probably my favorite example. Are you ready for it? Yes, Jenna.
So, just like another way to look at it, could we like look at it as like there's 10 teams, I'm gonna take my team out. Never mind. I was thinking about the
Okay. I haven't ever had anyone suggest another option. So if you think of another option, though, let me know, and we can discuss it and see if it will work.
Well, I guess in my head, when I read the poem, I was like, oh, I need to take out my team, and then there's 9 teams left. And that's how I pictured it. I don't know.
So that's what we're doing to get the 9 teams, right? Because my team, 1, plays all the other 9. Yes.
Okay, sorry.
But it still double counts everything when I do it that way, from that perspective, I think. Okay. So this question says, a store sells bicycles and tricycles. There are 15 cycles, right, bikes or trikes, in the store, and there are 35 wheels on those cycles. How many of each type of cycle are in the store? Okay, so it sounds funny because the way we're shortening the word to cycle, I get that, but yeah, bike and trike. But you can't say bike because it's a tricycle, right? So it sounds a little funny. This should probably feel like something you probably saw like in algebra and you made equations. Did it feel like that? Yeah, I mean, that's how it feels. I want to show you a very interesting approach to a problem like this that very young kids can actually do, and that there's no equations involved. Does that sound good? Okay, now, here's my drawing. This, by definition, is a bicycle. Okay? You already know now. I don't draw. This is a bicycle, and it has 2 wheels. Well, I know there are 15 cycles, right? So there's 15 of these bicycles that I'm going to start out by drawing. And you can too. Do I have 15? I think there's 15 there. Okay. So if they were all bicycles, I would have drawn it correctly. There's a problem, of course, because how many wheels are currently represented in this diagram? 30. And how many wheels are there supposed to be? 35. 36, or 31, 32. 33, 34, and 35, and those are my tricycles, because they now have 3 wheels. I have 15 cycles, right? 15 modes of transportation. I don't think you're going to go anywhere on something that looks like this, but there's 15 of them, and there are 35 wheels. So this picture accurately represents the number of cycles and the number of wheels, and hopefully by looking at the picture, you can count for me and tell me, how many bikes do I have? How many? 10. There are 10 bikes. And how many trikes? 5 trikes. Isn't that clever?
Yeah, that's good. I never thought to do
Yeah. Yeah, it's a fascinating example of making a diagram in a place that you might not have thought to make a diagram, but it works really well. Any questions on that? Okay. The next one is a type of problem, and I know you've seen these before too. And you've probably done it with equations. And again, I want to show you another perspective. So we have 48 feet of fencing, and we wish to make an enclosure along a side of an existing barn. What lengths would the sides need to be to have the greatest area enclosed for our chickens? Okay, so we are going to do a couple of things. This one's a strategy guess and check. I wanted to show you a guess and check strategy one. But to start with, before I guess and check, I want to draw a picture to make sure we have the right image in mind of what's happening. And our guess and check, remember, is really only effective if we do it in some kind of an organized way. So I'm going to make a list or a table as I guess and check to try to keep us organized. Okay? So first, the picture. All right, so we've got a barn. So here's my barn. And I want to make an enclosure using one of the sides of the barn. So in other words, I don't want to do this. I'm going to draw it big and fat so you can see it. I don't want to actually just draw another rectangle next to it, because what I really don't have is I really don't have any fencing where this line right here is, because that fencing isn't necessary because it's against the side of the barn. Does that make sense? So what I want to do instead is I will draw this so that I only have 3 sides of an enclosure. Pretend it's more rectangular. Mine's a little wobbly, but I think there's a good enough idea there. So hopefully you remember with rectangles that you have opposite sides that are equal to one another. So that's important information as we're thinking about it. And we want to have a lot of area, but we want to use our fencing well too. So, I mean, one option is that it looks kind of like this, right? Another option is that maybe it's really long and skinny, right? Or maybe it like protrudes really far out here. Like those are the sort of visual pictures that it could be, and we don't know which one it is. For the sake of argument, we just need to draw one, and then we're going to do some calculations to decide, okay? But we do know that whatever we put on the top part, the way I've drawn it here, is going to be the same as on the bottom. And then we've got this third side over here that may or may not be equal to the other two. Everybody good? Okay. Now it said we had 48 feet of fencing, right? And we're just going to guess something, okay? So somebody throw me out a number that we're going to put on the top and the bottom. 12. That's actually what I was thinking of trying to. So if I put a 12 here and a 12 here. So how many would that leave? How much fencing would that leave for my missing side? 24. Okay, so here are my options, right? I'm trying to find my length, my width, and I have to make sure that when I add those together, you know, I'll call the 12 my width. So I'll take my length plus my twice my width. I just want to make sure that those add up to 48 every time. That's my concern, right? I want to make sure that whatever I'm guessing, they add up to 48. And I need to figure out what my area will be of my shape. Do you remember what the area formula is for a rectangle? Yep. Length times width. Length times width. So the guess that we've had so far is that I have length and I have, sorry, I wrote that wrong. Length was 24 and my width was 12. And if it helps you, you can actually remember to put your 12 here twice so that you can remember I've got 2 widths. That's fine. That adds up to my 48. And then to find my area, I need to do 12 times 48. So this is my first guess, 12 times 48. So what is 12 times 48? I don't mean 48. I meant to put in 24. I'm sorry. Get my numbers all mixed. 12 times 24. What is it? 288. Okay. So we have to decide, is that the best option or is there a better option? I mean, it's definitely an option, right? So I need to try something else. And let's go ahead and just worry with the W, and then we'll alter things from there. So if I didn't have a W that was 12, what might I have instead? 4. Okay, we can try 4. So if I put a 4 here and a 4 here, so this would make it a long, skinny enclosure. How many feet of fence would be left for the length? There'd be 40. So 40 times 4 would be my area. 40 times 4 is 160. So that doesn't seem to be a good option. Long and skinny apparently did not give me a great option. But that doesn't mean that it couldn't still be something between 4 and 12 or still something more than 12. So somebody give me another choice. 20? So I do 20 and I do 20 here. And that would leave me with 8. So I have 20 times 8. And oddly enough, that gives me 160 again. So 20 times 8 isn't quite as long and narrow, right? I mean, it's not the same shape as the first one. It is a rectangle, but it's not the same shape. But it didn't actually end up giving me any better of an area. So I think we could probably at least say that when we increase the number or decrease the number a lot from 12, it didn't seem to be a good choice, right? I got something smaller. So how about we check something a little bit closer to 12 this time? Somebody give me an example. 10, 12, 13. Okay, let's do 10. Somebody said 10. So if I do 10 and 10, what's my missing amount? That's 20. So I have 18. Is that right? Oh, it's left 28 rather. Yeah, right? 28. So that's my 48 feet of fence. So now I have 28 times 10. How much is that? 280. Still not better than 288, but it's really a lot closer than the 160s were, right? So 10 seems like it's a really good choice in terms of it's closer to a bigger number, right? So closer to 12 was better than further away. More than 12. So can you give me an example?
13.
Okay, let's try 13. 14 would be fine too, but I heard 13 first. So 13 and 13 would leave what? Is it 22? Yeah? Okay. That's my 48 feet. So now I have 13 and 22. What's that one going to give me? 86. 286, yeah. $286. It's really close, and it's only one away, right? So there's really only one possibility left to check to ensure that we really think that 12, 12, and 24 are our best answer. What have we not checked that we perhaps should? 15's further away. So take a look here again.
11.
Yeah, 11. So 12 to 13 is only one away, and it's one bigger, right? When we were 2 away and 2 smaller, it was more different, right? It was smaller than 2 away. It was 8 away? Yeah, 8 away. So the only other thing that's equally close is the number 11. Everything that gets further away from 12 seems to be getting further away from the area that we are trying to optimize. So let's try 11 and 11. What does that leave me with? 26? So 11 and 26, what does that give me? 286. So our first guess was the best one, all right? It is the one that gives me the best or the biggest area, because that's what I'm looking for, the 288. But I have to try some other things to know. I mean, there's no way I would know if that's the biggest area, right? So we're doing a little bit of trial and error, but as we're doing it, we have to make educated guesses. So could we have tried 15? We could have tried a whole lot of other numbers, but there has to be some method to the numbers we're picking. Are we getting further away, or are we getting it to be bigger? And if so, it's bigger, how much further bigger can I get, kind of thing? All the questions we should be asking. So remember what the question asks, because that's always really important. We found what we think the answer is. It's this 12, 12, 24, and I've got 288 square feet. But the question it actually asks are, what lengths would the sides need to be, right? That's what it asks for, the lengths of the sides. So what are the lengths of the sides? 12 feet 12 feet, and 24 feet. Now, alternately, it could have asked me what's the largest area that it could have. I would be the same question. I just need to answer the part of the question that my answer already contained, and then it would be the 288. One thing to notice, because I didn't mention it yet, these answers all right here are feet times feet. So if that were my question, this would be square feet as my unit. So as we're working these problems, if there are units on the problem, there should be units in your answer, right? So the answer is not 12, 12, 24. It's 12 feet, and 24 feet. Okay, any questions on that one? Okay. We talked briefly about working backwards last time, and I gave the example that you've done this before because you've always looked, I mean, everybody's done it. You look in the back of the book, you see what the answer is. It doesn't match your answer, and then you got to go figure out how they got that, right? So this is an example of working backwards where the strategy is very obvious that you might want to pick this because of the way the problem is structured. One winter night, the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature's numerical value had dropped from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. What was the temperature at midnight? So what we actually are told is how the temperature is changing a bunch of times between one time and another time, and we're told what we are left with at the end, and we've got to go back to what happened at the beginning. Does that make sense? So it might be a good idea first to make a list of the times that they tell you. So what's the earliest time that they reference?
Between midnight and 5 a.m.
Right, so midnight, right? Midnight's their first time. And then you're exactly right, the second time is 5 a.m. What's the time that they reference after 5 a.m.? Yep, 9 a.m. And then noon. And we actually know what the temperature is at noon. It's 32 degrees, right? So I'm going to make a column. So even as I'm doing my working backwards, my mind thinks in lists. So I organize my work a lot like that. That doesn't mean you have to organize yours that way, but it is an option. I know my temperature is 32 at the end, and I also know what I really want is the beginning temperature. So let's actually read through the instructions again, and we're going to work from midnight down, and I'm just going to write how things are changing. I'm going to make a note on that. So from midnight to 5 a.m., what does it say happens? So it goes down 15. So it's like we're going to subtract 15, right? Okay. And then what happens between 5 and 9? It doubles. And I'll talk a little bit about why the phrasing is a little awkward sounding in a minute here on that one. And then what happens between 9 and noon? It goes up 10, right? So it adds 10. And what do you suppose doubles means? Yeah, it multiplies by 2. So my operations are, if I knew where I started, I would go down 10, I'd go down 15, subtract 15, I'd multiply by 2, and then I'd add 10. But if I'm going to go backwards, what am I going to do? Yeah, everything in reverse. Okay, so we've got my 32. You guys are already telling me. So 32, what will I go back up to if I go up to 9 a.m.? 22, yeah. It's 22 then. So what will I do to get to 5 a.m.? Divide by 2 instead of doubling by 2, right? Which would get me at 11. And then what would I do to get back up to midnight? Add my 15, which puts me at 26. So the answer is 26. It doesn't really say it in the problem. It's degrees. I don't think so anyway. Does it say Fahrenheit? No, it has to be Fahrenheit or it doesn't make any sense. But it's 26 degrees because it does say degrees. So at the very least, I got the degree marker on there or the word degrees. I just wanted to make one comment because it sounds funny, and I want you to know the reason that it's written to sound funny. It says the temperature's numerical value. Did you guys think that sounded awkward? It's a weird way of describing it. But temperature is really awkward sounding because to double the temperature, what does that mean? Like, what does a double heat value mean? Well, first of all, it means something different if you're using Celsius than if you're using Fahrenheit. Right? I mean, you can double numbers, but it doesn't really, how do you double a temperature value? Right? It feels twice as hot. What does that mean? It feels twice as hot. That doesn't have any real meaning. But I can double numbers, so that's why I said double the numerical value. That's why it felt a little awkward. So it's 26 degrees. Okay. The last thing that we're going to do, because it actually applies to a group work problem you have, is take a look at the 12 days of Christmas, because you may or may not remember them. And there's actually religious symbolism in the 12 days of Christmas that you may not realize, which is kind of cool. So part of the reason, again, we're looking at this is because I want you to see it's a partridge in a pear tree for number one, but it's the doves, the hens, the birds, the rings, the geese a-laying, and so forth, because all that's going to come into your homework. You're going to need to know the order, okay? But just to kind of give you a fun trivia fact, I think, kind of. The 12 days of Christmas have symbolism. So the first one, the partridge in a pear tree, is true love, and that's God. The 2 turtle doves represent the Old and New Testament. The 3 French hens are faith, hope, and love. The 4 calling birds are the 4 Gospels. Your 5 golden rings are the Pentateuch, the first 5 books of the Old Testament. Your 6 geese of laying are the 6 days of creation. 7 swans of swimming are the 7 gifts of the Holy Spirit. Your 8 maids of milking are the 8 Beatitudes. Your 9 ladies dancing are the 9 fruits of the Spirit. The 10 lords a leaping are the 10 commandments. The 11 pipers piping are the 11 faithful apostles. And then the 12 drummers drumming are the 12 points of doctrine in the Apostle Creed. Isn't that cool? Yeah. So, and now you have your list for that problem as well. All right, so we're going to split you into groups. We're going to work on some group work in class, and then we're going to have this homework due when we come to class next time.